Hi, I'd like to tell you about this formal semantics that we've been developing. Before getting to why we are excited about it, let me introduce the programming language that we formalize. I suspect you've heard about the LLVM compiler infrastructure before. It's well known, for instance, to be at the center of the C-Lang compiler, but really it has been used for a variety of both academic and industrial projects. It's a humongous project as a whole, but in particular at its core is a programming language, the so-called LLVM IR for intermediate representation. This language has been designed to be extremely suitable for analysis and program optimization while being low-level enough for backends. It's a control flow graph-based language in so-called single static assignment form with low-level instruction. So it looks simple enough. However, one hint that is not that simple is simply to look at the amount of work that our PL community has performed to try to formalize this language. In particular, a huge variety of works have been looking for understanding and formalizing the semantics, or simply some aspect of the semantics. But even just understanding the memory model has proven to be particularly tricky. And this kind of line of work have given rise to very principled tools to find bugs in LLVM as such. The specific line of work that we are based on in particular is called Velum, a project that was started in 2012. The idea of Velum was to provide a formal semantic in the Hoc proof assistant of LLVM IR. It was a success, a significant success of language was formalized, and even better, complex optimizations have been proven with respect to these semantics. But after this initial success, Velum has proven extremely hard to evolve, and in contrast, LLVM IR was evolving extremely fast. So in a sense, the gist of this paper is to provide new foundation for Velum, to revive it, and to do so under this idea that we would like to have a project able to keep up with a realistic language. There are of course many answers to such a difficult problem, but the angle in particular that we will take here is a semantic angle. So let me give you a very rough approximation as to how the semantics of Velum used to be shaped. The idea is to be parameterized by the whole programs with respect to which you are considering the semantics. Let's call it G for graph, and to use program counters to know dynamically where inside of this graph you are currently executing. Of course, you will also thread the memory. The first thing that we don't like with this approach is that if you consider a program transformation, you will of course modify G. We will therefore have to relate two programs with respect to basically two different semantics, and we will have to design invariants that explain how these program counters relate before and after optimization to compensate. More generally, you lack compositionality. Another aspect is that a single relation is encompassing all the aspects, all the effects of your semantics. If you modify one part of it, it's therefore extremely hard to know what part of the development will break. You lack modularity. And finally, intrinsically, this semantics does not compute. It is a relation. It goes into prop in the Hoc lingo. It therefore lacks executability, and if you want to perform testing, you will have to work extra hard. In this work, we therefore rebuild Velum with completely different semantic tools. We use interaction trees, which are a library introduced last year at Popol. The idea of interaction trees is that a computation, it's dynamic, is represented as a potentially infinite trees. If you consider here, for example, a computation that may interact with a state, you will therefore potentially have silent steps that you do not observe in your computation, but also observable events that are essentially requests to the environment to answer a question. What value should I get if I read X? Depending on this value, a continuation will explain how the computation will continue, for instance, terminating by returning a result, or potentially diverging. More specifically, if we try to understand how one can use interaction trees to give the semantics to a language, the idea will be in two steps. In the middle part, you have the representation of your program as one of these trees. Here, for instance, consider a program that will write a certain value to X, then read back from X, and write whatever value you get back to Y. Of course, intuitively, you expect your read to X to get 1. However, at this stage, events do not have any semantics. That is in the second part, that's very much the style of algebraic effects, if you're familiar with that. The handler will define the semantics of these events. The semantics defined in an appropriate monad, so that after this phase of interpretation, you obtain a computation that now can reduce. You couple that with the first phase, where the syntax of your program is represented as one of these interaction trees. You therefore get at a high level a general recipe. If you want to define the semantics of a language L, write, of course, its syntax, but then inventory the effects that your language may have. You will categorize these effects into various interfaces, and you will put them together. Then you will represent the syntax as this non-interpreted interaction trees over this event interface. The library will provide combinators that help you do so in a compositional way. After that, each of these categories of events are implemented in an appropriate monad. And because you handle each of these categories of events separately, you obtain some modularity. Finally, because interaction trees do not go into prop, they are a co-inductive data structure, you may still extract the result and get an interpreter that you can execute in OCaml. Now, one of the messages of this paper is that this simple recipe essentially scales. In the case of LLVM-IR, inventorying the effect leads to this signature made of 9 domains of events. And for instance, behind this ME is hidden all the interaction with the main model. I will not be able to describe how we represent the syntax as one of these trees. All the details are in the paper if you're interested. But the message is that these combinators are expressive enough that you actually are able to do the whole job. Finally, I would like to give you a little idea from a bird's eye view of the structure of the semantics once you handle all of these events. The idea is that you start from the syntax, as we said, of VIR, and you will first have this structural representation into one of these non-interpreted trees. But from there, you will basically build a stack of interpreter that will peel away each of the effects incrementally. First, you implement what is called intrinsic, a peculiarity of the language, and then you start introducing the pieces of state that you will manipulate. The global environment first, then the local environments, finally the main model, and here you have a handler that is isolated that implements the whole memo model with respect to which reason. At this stage, an interesting phenomenon happened. It turns out that LLVM-IR, because of so-called undervalue and undefined behaviors, is not a deterministic language. We therefore capture in a propositional model all of the legal executions by defining 2 specific handlers. However, I told you that we want it to be executable, so sharing all of the semantics except for these 2 handlers, we define 2 alternate handlers that are executable and that will be used in order to get a reference interpreter. Because we share so much of the semantics between both of the executable interpreter and the propositional model, we essentially get for free a refinement proof showing that the executable interpreter exhibits a legal behavior with respect to the model. At this stage, we have defined a formal semantics, but an important question is to ponder whether there is any relationship between these semantics and what we were interested in modeling, that is LLVM-IR per se. Of course, to answer this question, we leverage this is that we have to test because of this extracted interpreter. So we have an unverified parser that takes a valid LLVM-IR syntax as input, feed it to the extracted interpreter, and finally feed the resulting tree to obtain the OCaml driver that will crawl the tree to extract the result. We cover a realistic sequential subset, and are, of course, happy to take feature requests. We have performed some differential testing against Ceylon over a collection of manually written unit tests, a handful of significant programs that come from the front end, but also some randomly generated programs. Now, this is about fidelity. The other question is whether this semantics is any more useful than the previous one. One reason we believe so is that interaction trees come with a notion of weak bisimulation that correctly characterize when 2 computational represented trees are equivalent. Through this representation function that we have, we therefore get the first notion of equivalence of programs. And this notion of equivalence of programs is playing well with the compositionality of the semantics, allowing us to have a battery of structural equational lemmas that characterize the semantics of the language in terms of its syntactic subcomponents. In particular, we can reason about open control flow graphs. For instance, here illustrating on a simple example, the semantics of a control flow graph can be reduced to the semantics of one of its subcomponents if we check whether syntactically or through a more semantic proof that there is no way to re-enter the other part of the graph. In the paper, we illustrate the use of this equational theory to provide a quite satisfying proof of a simple block fusion optimization. Now, if we come back to the structure of the semantics, that was organized as this stack of interpreters that introduce progressively into state monads pieces of the state and then the propositional model. Well, it turned out that this structure corresponds also to a stack of refinement relations that are included one into the other as a stack of growing relations. When you introduce a state, you get, therefore, a notion of equivalence in this monad. And then when you introduce a propositional model, you start working up to state inclusion. Interestingly, the block fusion proof does not depend on the state at all, purely in terms of the control flow. And it can be established at the very first level before giving any semantics of the state events, and therefore before introducing any concrete state. However, because of this stack of inclusion, the result can be transported all the way down. Now, of course, in general, you are interested in reasoning about the state concretely, in particular when you want to understand the semantics, of course, of your instructions. Since each instruction is implemented as a non-trivial tree, what we do is to provide an abstraction. We give equationally a characterization of the semantics of each of the instruction in an axiomatic way. Once we have done that, we can make the representation function completely opaque and reason more at a higher level of abstraction about the language. Concretely, it gives us two main reasoning ingredients. The first one is this combination of strong equivalences that we have at the VIR level. We have equivalences about the syntactic structure of the language, about the control flow, but also about the instruction, expression, and terminators. When we put all of this together, it gives us some kind of symbolic interpreter that we can run by rewriting during any refinement proofs. Actually, these refinement proofs can be performed from VIR to VIR, but also in an heterogeneous way when interfacing with other languages for a front-end or a back-end, for instance. And in particular, when we do so, what we get is a primitive relational program logic that, in particular, is compatible with this symbolic interpreter. We are therefore able to combine both of these ingredients to have interesting compositional construction of refinement proofs by equational means. We have been conducting a major case study in order to validate this approach. Helix is a formalization of something called Spiral that is a pipeline to generate high-performance code for numerical computation. Helix is a formalization in Hoc of Spiral and chose to target Velum as its backend. In itself, it has a complex compilation chain that is using diverse techniques to ensure correctness. But at the very bottom, its last intermediate representation, called FHCall, targets Velum, our formalization of LLVMIR. In order to prove this last pass, that is a compilation from a high-level language down to LLVMIR, we have used this technique, giving a semantics based on I-trees to FHCall, proving it equivalent to its previous semantics, and using this technique combining equational rewriting with relational program logics in order to prove the correctness of this compilation path. To wrap up, this paper is about the revival of Velum, a formal semantics to LLVMIR formalized in the Hoc proof assistant. This new version of Velum is based on a semantic tool called interaction trees that we use in order to gain interesting properties, compositionality, modularity, and a verified interpreter for free. Furthermore, reasoning about semantics allows for a very compositional and equational style of proofs for refinements. Of course, defining formal semantics is just the first step. Now that this foundational ground is laid, we are excited to apply it to various use cases, but we would be even more interested if any external contributor would love to join us in this adventure.
Hi everyone, and thanks for tuning in to my talk. I'm Alejandro Aguirre, and today I will present our work on reasoning about adversarial computations in a probabilistic higher-order setting. Let me motivate the problem using a data structure known as a Bloom filter, which is used to represent a set of elements from some universe X. Internally, they consist of a bit array of length d that is initially set to 0, and a number of hash functions with codomain 0 up to d-1 that are selected at random during initialization. Bloom filters accept insertion and membership queries. When inserting an element x, we compute the hashes of x and we use them to access the array at the corresponding indices and set those bits to 1. If when inserting an element we get the index of a bit that is already set to 1, we leave it there. For membership queries, we again hash the element to of the indices and check if all the corresponding bits are set to 1. If so, we return a positive result, otherwise a negative result. This representation is efficient both in space and time, but membership queries may return a false positive due to a hash collision. This last point motivates a family of attacks known as pollution attacks. The idea is that an adversary makes a number of insertion queries and tries to set as many bits to 1 as possible to increase the probability of a false positive in a membership query. So after n insertion queries, we may ask ourselves, what is the probability of a false positive? Or a related question, what is the expected number of bits that will be set to 1? Both of these are adversarial properties. Generally speaking, adversarial properties study the behavior of a program or an oracle with private memory with respect to an unknown adversary. The adversary gets to perform queries in an adaptive manner, choosing the inputs of new queries after seeing the outputs of previous ones. Moreover, we differentiate between two kinds of properties. The probability of a false positive is qualitative, in the sense that it's an event that either it happens or it doesn't. Meanwhile, the expected number of ones is quantitative, because it is a quantity that we can count. With this motivation in mind, we can set the goals of our work. First, we want to have a way to reason about both qualitative and quantitative properties of probabilistic programs. And we will do it in a higher-order setting which provides a natural way of modeling adversaries as higher-order functions. But we need to restrict adversaries in two ways. We need to have a maximum number of times that the adversary can access the oracle, and moreover, we need to separate the memory of adversaries from the private memory of oracles. Our solution involves the following contributions. We begin by introducing a type system based on a graded state monad and effect polymorphism that is used to restrict the capabilities of adversaries. Then we develop unary and relational logics to reason about programs in the language. The unary logics support both reasoning about quantitative and qualitative properties. The relational logic, which I will not present today, is based on the notion of probabilistic coupling and can be used to prove relations between programs such as equivalence of probabilistic programs, approximation, or differential privacy. To these logics, we add inference rules to reason about adversarial properties, exploiting the restrictions induced by the type system. Finally, we present a unified categorical model to prove soundness of all of our logics. The language to consider is a simply typed lambda calculus that we extend with terminating recursion, first-order state, and probabilistic sampling. Terms and types are mostly standard. We will use a monad T to represent effectful computations, which send an initial memory to a probability distribution over final results and memories. And here we use the letter P to denote probability distributions. Memories are maps from locations to first-order values. These computations are constructed using the usual unit and bind term formers, plus specific operations for reading and writing the memory, and for sampling random values. In particular, unit of T is going to be the computation that does not change the memory and that returns T with probability 1. and bind sequences to computations by using the final memory and result of the first one as inputs for the second. The first thing we do is we introduce a graded state monad. This adds some additional information to the monadic types in the form of two parameters. The first one, capital sigma, is a set of memory locations. It should be understood as an over-approximation of the locations that the computation can read or write on. The second one, k, is a multiplicity that is meant to count the number of calls that are made to an oracle. The typing rules for monadic constructs need to keep track of this information. So in particular, the unit rule introduces a computation with no cost and no footprint, and the bind rule adds the costs and the footprints together. So note here that the rules in fact act like the unit and the multiplication of a monoid. The rules for other constructs, such as reading or writing, need to add to the footprint the location that they use. The next step is to add effect polymorphism. By this, we mean that we allow universal quantification over grading variables representing the memory footprint. Terms will then be typed over a grading context psi and a typing context gamma. We show here the rules for introducing and eliminating universal types. So concretely, if tau is a type that is well-formed under a grading context containing the variable alpha, and T has type tau under a context gamma that does not contain alpha, then T can also be given the type for all alpha tau. And the rule for elimination is dual. The point behind this quantification is best justified by showing how adversaries are typed. So for us, an adversary is going to be a computation whose type is given by the pattern shown here. Their input is an oracle whose memory footprint is some abstract alpha and whose cost is 1. The memory footprint of the adversary is sigma union alpha and its cost is k, and then the whole type is quantified by alpha. This here contains all the information that we need to constrain the adversary. So first, we can see that it may call the oracle at most k times, since the cost of every call is 1. And second, the parametricity induced by the quantification means that every effect that the adversary has directly on the memory must be in sigma, and any other effect needs to be through an oracle call. This is because the adversary cannot inspect alpha itself and then must behave the same no matter what alpha is instantiated to. In order to write and prove specifications about programs in this language, we introduce 3 program logics. Here I will showcase a generic qualitative logic. Judgments in this logic have a shape that is reminiscent of for logic. We have a computation T that we want to reason about, a precondition P, and a postcondition Q that is also indexed by a real number delta. Here, the precondition P is an assertion that may contain a distinguished variable S representing the initial state. Similarly, the postcondition Q is another assertion containing a variable S representing the final state and a variable R representing the final result. However, the interpretation is not as straightforward as in for logic. Here the output is probabilistic, so the actual meaning of the judgment is that if the precondition P holds for the initial memory, then the output will satisfy the postcondition Q, at least with probability 1 minus delta. Or in other words, the judgment can fail to satisfy the postcondition with probability delta. The important thing to note about the judgments is that P and Q are plain Boolean assertions that do not mention probabilities. Probabilities appear in the interpretation of the judgments, but never in the assertions themselves. In this way, we hide away most of the explicit reasoning about probabilities, and we can reason in a more natural way. This is an example of a lifting, which is used to use plain assertions to reason about probabilistic programs. The paper presents inference rules for every construct in the language. As an instance, we present here the rule for binding. So suppose we have two computations, T and U, and we want to sequence them. So first, we prove a judgment for T, stating that with precondition P, we can ensure postcondition Q with probability 1 minus delta. Then for U, we prove that with precondition Q, we can ensure postcondition R with probability 1 minus delta prime. Then the bind rule lets us conclude that with precondition P, the sequence TU satisfies the postcondition R with probability 1 minus delta prime. This is analogous to the sequence rule from Hoc logic. Once again, note that the rule itself has no explicit reasoning about probabilities, because P, Q, and R are standard assertions that do not mention probabilities. We only need to add together the gradings, and this is enough to track the probability of satisfying the postcondition. The adversary rule instead formalizes a reasoning principle about adversaries. This rule lets us prove a property that a term T has when interacting with an abstract adversary A, of which we only know its type, but not its implementation. Concretely, A has a type of adversaries we introduced earlier in the talk, which ensures that it only writes to sigma, and that it calls its argument at most k times. Now suppose we have some invariant phi that does not depend on sigma. If using our logic we can show that T preserves phi with probability 1 minus delta, then it must be the case that A, when instantiated with T, must also preserve phi with probability 1 minus k times delta. This is a consequence of the type of A, because the only chance A has of breaking the invariant is through oracle calls, but it can perform k calls at most, each with a probability delta of breaking the invariant. This here is a very general rule that assumes very little from the adversary and lets us prove how T behaves with any inhabitant of the adversary type. In the paper there is more material that I have not covered in this talk. We present two other logics. One of them is a generic quantitative logic that is intended to reason about expected values. This can be obtained as a direct generalization of the qualitative logic, keeping most of the inference rules unchanged. The only thing we need to change is that assertions become instead real-valued functions, and the logic will reason about their expected values. This generalization works because the logic can be interpreted in any complete Heyting algebra, such as the positive reals. We also present a relational logic that uses probabilistic couplings to reason about relations between programs. These logics are all illustrated with examples. Finally, we present a unified semantical model for the logics. The model is parameterized by a choice of Heyting algebra to interpret assertions, plus a lifting that maps assertions over plain programs to assertions over probabilistic programs. If you are interested in learning more, please read our paper, and I will also be happy to answer questions in the Q&A session. Thanks for your attention.
Okay, there are a lot of different approaches to gradual typing around these days, all seemingly different. So how are we to make sense of this space? Well, the research community has come up with 3 semantics to capture the key differences between most of these approaches. The Erasure Semantics, championed by industrial systems, uses types for type checking and then throws them away to run the program as if it were fully untyped. Thus, any mismatches between type annotations and actual values not caught statically manifest as errors from the runtime, accompanied only by a stack trace to help developers track down the mistake. The other 2 semantics come from the academic world, and they try to help programmers by inserting dynamic checks to verify that values match up with annotated types. Furthermore, the semantics offer special failure information called blame that identifies parts of the program as being related to the type-value mismatch. That said, the 2 semantics perform the dynamic checks differently and provide very different kinds of blame. In the face of these 3 semantics, I want to pose a research question. How do these semantics help programmers find the source of type-value mismatches? Of course, this question has been investigated before. From extensive theoretical work developing and analyzing the semantics, we've learned that the semantics offer different kinds and degrees of guarantees for detecting type-value mismatches and for blame. But it does not tell us exactly how these guarantees translate into practical benefits for the working programmer. Then, extensive performance work has shown how those guarantees come at sometimes extreme performance penalties, but not whether the costs are justified by debugging benefits. There's also been a little work analyzing user preferences, which suggests that users prefer semantics with stronger guarantees. But of course, it's not clear how general that preference is. This work develops a new method called the Rational Programmer, which taps into aspects of all 3 of the other approaches that we've just seen. The key idea of the method, inspired by the economic idea of Homo economicus, is to simulate an idealized programmer using a system in real-world conditions. By testing the simulation in a large and varied set of situations, we can understand the pragmatic strengths and weaknesses of a system. To make this concrete, the Rational Programmer for gradual typing will simulate a programmer with a gradually typed program that, when run, produces a type-value mismatch error, and will try to use it to locate the source of the mismatch in the program, using blame or whatever other information is available. Specifically, the simulation will follow an algorithm that looks like this. First, it will run the program to get a type-value mismatch error. Then, it will identify the blamed module. Next, it will type the blame module. And finally, it will type check the program. And if it gets a type error, then the algorithm terminates, and we say that it succeeds at locating the mismatch. Otherwise, it goes back and continues from step 1. And if it doesn't eventually get a type error, then we'll get stuck there here, trying to type the blame module, perhaps because it's already typed, as we'll see later. If this happens, the rational programmer fails to locate the mismatch. And so these 2 steps form the possible success and failure termination conditions for the simulation. Now, using this simulation, we can design an experiment to evaluate how often the rational programmer succeeds at locating the source of type-value mismatches in a corpus of debugging scenarios from real programs. The experiment essentially consists of running the rational programmer on all of the scenarios and collecting its successes and failures for analysis. Of course, there are 3 different semantics that we want to analyze, so we run this experiment on 3 versions of the simulation using each of the 3 semantics, which we call modes. And then at the end we can compare the success rates of each mode to understand which semantics offers more useful information for the rational programmer to locate the source of type-value mismatches. And we'll do all of this in the context of Racket, using implementations of all 3 semantics based on typed Racket, and using debugging scenarios from typed Racket programs. But before we get into the details of the experiment, let's get some intuition for how the rational programmer works with each of the 3 semantics through an example. Here's the dependency graph of a card game program, which has modules defining components of the game like players, cards, and the dealer. And these 3 modules are typed, and the rest are untyped. To start a game, the main module creates a bunch of player objects and sends them over to the dealer to manage the game. The dealer module expects the players to have a start turn method, and throughout the game it iterates over the players to call that method on each one. And the player module defines the player class, but it has a mistake. The start turn method is misspelled. In other words, there's a mismatch between the player type that the rest of the program, and especially the dealer, expects, and the actual player values that the player module will produce. So let's see how the rational programmer will locate the source of that mismatch in this program by making those expectations manifest through type annotations. We'll start with the natural mode. When we run the program under the natural semantics, we get a contract error, which blames the player module. So the rational programmer will type the player module as a way of checking the expectations about its interface, and then the type checker can detect the mismatch and raise a type error. So the rational programmer succeeds using the natural semantics. Next, let's see the erasure mode. Running the program under the erasure semantics produces an error from the runtime, saying that there is no method named startTurn, and the stack trace identifies that the error happens in the dealer module. So the rational programmer will treat this as a kind of blame, and it will type the dealer module. The program still type checks, so the rational programmer runs the program again, and it gets the same error. And now it's stuck, because both of the modules identified in the stack trace are already typed. So this mode of the rational programmer fails to locate the source of the mismatch. Alright, finally, let's see the transient mode. Running the original program under the transient semantics produces the same error from the runtime as we saw before. So the rational programmer will again identify the dealer module from the stack and add types to it. Now the program has enough types that when run, it produces a transient assertion failure, which blames the player module. After typing it, now the program fails to type check, and so the rational programmer succeeds using the transient semantics. So now we've seen how the rational programmer simulation distinguishes between the information each of the semantics offers for locating the source of type value mismatches, and I want to make an observation, which is that blame seems to have been useful. Both the natural and transient modes were able to use blame to successfully locate the source of the mismatch in the example. But was blame really necessary for the rational programmer to succeed? In particular, both of these semantics provide blame in addition to dynamic checks, and it isn't clear if we can attribute the success to the blame alone. To understand this distinction, we can create new modes of the rational programmer, which use the natural and transient semantics, but ignore blame and instead just use the stack traces from check failures, and we can see how often these modes succeed compared to the modes that use blame, to tease apart the value of blame from checks alone. And in fact, this way of using modes gives us a very flexible way to add baselines and control for confounding factors in our experiment. We actually use even more modes in the paper to do things like analyze different ways of interpreting blame and comparing against the effectiveness of using a totally random debugging strategy. I won't get into the details for the sake of time though, so check out the paper for more. And now, before wrapping up, I want to quickly return to the experiment. So here's what we did. Starting with 10 typed racket programs from the GTB benchmark suite, we used mutation to create about 72,000 different debugging scenarios. And then we ran all the modes of the rational programmer on all of those scenarios, which took about 3.5 years of compute time total. Finally, we analyzed and compared the success rates of the different modes. Again, for the sake of time, I won't go into more detail about the experiment or analysis, and I'll just give a few takeaways. First, natural blame leads the rational programmer to success in about 90% of the scenarios. That said, natural blame only provides more useful information than transient blame in about 4% of the scenarios. And finally, erasure provides enough information for the rational programmer to succeed in almost 80% of the scenarios, despite not having any checks or blame at all. In closing, though, I want to step back and look at the big picture. The rational programmer is a new method for understanding the pragmatics of systems like gradual typing, and in this experiment it has given us a new lens into the pragmatics of debugging with the 3 different semantics. And overall, we think this experience has shown how the rational programmer is a useful tool to add to the toolbox of the working PL researcher. Thank you.
Hi, my name is Nick Generakis, and today I will talk about probabilistic verification of network control planes. This is joint work with Alexandra Silva and David Walker. The control plane of the network is a distributed system that computes the paths over which hosts connected to the network can exchange traffic. Network engineers issue a configuration for each switch in the network, describing which routing protocols should be used, setting the policy of the network, whether that is filtering some routes or setting path preferences. The problem is that it is challenging to coordinate a distributed system with these local configurations, especially since these configurations are often thousands of lines of code. So, operators have turned to network verification tools to ensure their configurations match their intentions. Before deploying a new set of configuration files, operators can use a static verifier to check whether their intentions are satisfied. And they can ask questions such as, can two hosts talk to each other, or does traffic always traverse a firewall in the network, or is connectivity retained when some links in the network fail? On the other hand, operators do not expect properties to always be true. Sometimes a switch might crash, or some links connecting two different parts of the network may fail. So the network's operation is subject to this probabilistic phenomena, and in practice, operators want to check that their properties hold with some very high probability, allowing for short violations of these properties. In this paper, our goal is to bridge the gap between the probabilistic specifications that operators use in practice and the deterministic answers that most existing verifiers focus on. And there are multiple conflicting objectives to achieve that, and we need to carefully balance them. First of all, there is a scalability issue when analyzing large networks. Usually the techniques which are fast either cannot reason about unknowns in the network, such as combinations of failures, or they only support a very limited subset of routing protocols, making them less useful in practice. Similarly, approaches which are more general, supporting multiple protocols, and also exhaustive reasoning about unknowns, do not scale well. We build on a functional language designed specifically to describe the routing behavior of networks. It's a very simple and conventional functional language. In fact, it's simpler than you might expect. It lacks some basic features such as recursion, but despite its simplicity, it allows us to construct very detailed routing models. And to model unknowns in the network, we adopt the approach of solver-guided languages like Rosette and allow the user to declare some values as symbolic, meaning that they denote any possibly well-typed value. In fact, users may also specify a distribution describing the probability symbolic equals a specific concrete value. Finally, to deal with the scalability issue that arises in complex networks, we separate symbolic reasoning, for instance, reasoning about whether a link has failed, from concrete computations, for instance, what is the route after applying the configured routing policy. In contrast, previous approaches will resort to performing all computations as symbolic computations. For example, SMT-based techniques will convert the problem to a logical formula and ask an SMT solver to find the solution. So let's look at a probabilistic network model in our language. Assuming we start with some device configurations, we can translate them into our language, describing the topology they define and the routing policy that they enforce. So this is what routing protocols are used and how they transform a route as it traverses a link between two switches. And these are simple transformations, such as increasing the path length or setting a tag on the route. The complexity comes from the very high number of rules that are used. In practice, the function describing the network's policy may be several thousand lines of code. Next, we will define a failure model for the network. In this case, we declare 4 symbolic Boolean values, which we will use to denote whether a node has failed, which we assume happens with probability 0.005. The function fNode associates its node with one of the symbolics we declared, except for node 4, which we assume cannot fail. The function failures captures what it means for a node to fail. Given a link, if either node at its endpoints has failed, so if the respective symbolic is true, then an empty route is returned. Otherwise, the policy of the network is applied as usual. Now that we have the model, what we need to do is come up with a way to efficiently interpret it. Because of the symbolics, these programs describe a huge state space, so we'll have to carefully navigate that. Okay, so first let's focus on symbolic computations. When we declare a symbolic, we get the set that includes all possible values for that type. To efficiently represent these potentially very large sets, we will use binary decision diagrams. In this example, F0 denotes the set that includes both false and true. As a BDD, we can represent the set inclusion function using a decision node F0, where if F0 is false, this is the dashed arrow, that leads to the true terminal node, meaning that false belongs to the set. And the same applies to the solid arrow, which represents the true value of F0. One of the advantages of binary decision diagrams is that they do not explicitly represent redundant decisions. So nodes that lead to the same result are automatically removed. Hence, in practice, we only need to store the terminal node true, which is one of the things that gives us a compact representation of this potentially very large state space. If we want to compute a set of values that describes that either F0 or F1 are true, then we can just directly do so over the binary decision diagrams. For the logical OR, if F0 is true, then this leads to the true leaf, because it belongs to the set. Otherwise, if it is false, then we will look at F1, and if that is true, then again this leads to the true leaf. Otherwise, this combination does not belong to the set, so it leads to the false leaf. On the other hand, when evaluating the network's policy, we could again convert everything into BDDs and work with this representation, and some prior work does this, but the problem with that is that we end up with very large BDDs, as routes require multiple bits to represent them. And then we have to perform operations such as addition over BDDs, which is very expensive. What we want to do instead is to use fast hardware-level instructions in order to process the routes. So we saw that the guard of the even else is symbolic, and that the branches are concrete. So what is the type of the computation for the whole function? In this case, we don't want to interpret it as symbolic, because then we'll be computing everything over BDDs, which is slow. And we can't really use a concrete computation because there is a symbolic computation in there. For these computations, we introduce the concept of a multivalue, which are concrete computations that rely on some symbolic computation. So whereas the interpretation of a symbolic we used is a function from bit vectors to booleans, a multivalue is a function that can return any type of value, in this case BGP routes. When applied to an edge, the function failures returns a function that takes as input a multivalue and returns another multivalue. We represent this using a variant of BDDs called multi-terminal BDDs, where the only thing that changes is that the terminal nodes can take any type of value, not just a boolean, so the diagram can have more than two terminal nodes. Given such a diagram as the input to the function failures, it will transform into a new multi-terminal BDD by performing a symbolic computation on the decision nodes of the diagram and a concrete computation on the terminal nodes. To distinguish between the different types of computations, we leverage the type system. Types are annotated with a computation mode, so in addition to the type of the value computed, they also give us information about the computation mode that is used. And there are some basic rules about how you can combine the different computation modes. You can almost always combine a concrete computation with a symbolic computation by interpreting the concrete computation as BDDs. And similarly, you can combine a concrete and a multivalue just by applying the concrete computation on the leaves of the multivalue. And obviously, every mode is compatible with itself. But the key idea is that multivalue computations and symbolic computations are incompatible. You can't use one where the other is expected. If this was allowed, then we will have to convert the multivalue to a BDD, and then all operations will be over BDDs, and we will lose any performance advantages. There's only one way to combine a symbolic and a multivalue, and that is to condition the multivalue using the symbolic, as we do in the example above. Obviously, this is constraining the type of programs you can write. There might be some programs that you want to write, but you cannot. But that is the trade-off for faster executions of the programs that do type check. We implement the different computation modes via a translation to a lower level language that exposes various BDD and multi-terminal BDD primitives, which we have implemented in OCaml on top of a conventional BDD library. The type system guides the translation, and we have proof on paper that when the translation is applied to a well-typed program, it produces a well-typed program in the lower level language. To recap, given a model in ProbMV, we can simulate the routing process, computing for each node the routes it has learned under different failure scenarios. And once the simulation has completed, we can check network properties by computing Boolean expressions over these routes. For instance, checking whether or not a node has a route to the destination, we just need to assert that the optional value is constructed using the sum constructor. Finally, we can combine the computed assertions with the distributions of the symbolics, which we also represent as decision diagrams. And using a weighted model counting algorithm, we can compute the exact probability that the assertion is true. This design was key to scaling the verification process, because simulation is already computationally very expensive. If we were to mix reasoning about probabilities in the simulation process, then we conjecture will only be able to verify very small networks. And note that we're not interested in the intermediate states of the simulation, so computing probabilities during the intermediate stage would be another slowdown of the whole process. We evaluated our tool on ISP and data center networks. These two have slightly different properties. ISP networks tend to have less symmetries and less redundancy, but richer policy, while data center networks are generally larger but have very symmetric design. The table shows one ISP and one data center network evaluated against two different failure models. One where all the nodes can fail and one where all links can fail. In both cases, the route computation is what dominates the verification time. Computing probabilities and checking assertions is very fast. You might also notice that for each network and failure model there are two experiments. The difference is in the ordering of decision nodes we choose. It's well known that picking a bad order can blow up the size of a decision diagram, but there's also no efficient way to find an optimal ordering. Usually, a good ordering is motivated by the application. So in this case, we tried a random variable ordering and an ordering that's based on a breadth first search from the destination node. Intuitively, a failed node or link that is close to the destination will have larger impact than a failure far from the destination. The BFS ordering, as you can see, worked much better than the random one, and this is reflected in both the computation time and also in the size of the decision diagrams generated throughout simulation, where there is at least an order of magnitude difference. In the paper, you'll find more details about how our type system and the implementation of the various computation modes work. You will also find more details about how our weighted model counting algorithm works, and in particular for symbolics that require multiple decision nodes like symbolic integers. Finally, we also discuss a new simulation algorithm that we devised in order to optimize the number of steps required for simulation to converge. Currently, one of the drawbacks of our approach is that we don't support observed statements, which are fairly standard in probabilistic languages and allow you to condition one distribution over another. It's not obvious how to do this with our approach, and an interesting question is to find the conditions under which we can do it efficiently. Thank you for your time.
Hi everyone, I'm from Text to Speech. On behalf of Manuel Serrano, I'm going to present the paper titled Of JavaScript Ahead of Time Compilation Performance. JavaScript is particularly difficult to implement efficiently, because most of its expressions have all sorts of different meanings that involve all sorts of different executions that are not distinguished by any syntactic or type annotation. Let's illustrate this with this simple example. Most C programmers would know that this loop is compiled with a couple of registers and a conditional branch. But what if we are now turned into JavaScript programmers? This is a all different story, because it all depends on A can be an array as before. But it could also be an object, provided it has properties named length, 0, 1, and 2. A could also be a sparse array, or even an array with one property holds by its prototype. Even worse, if we modify the increment, the loop can also be used with radically different indexing. The difficulty is there. The same code can be used with many different data structures. So this raises the question: does it make any sense at all to try to compile statically such a language? Or even more fundamentally, why trying? There are actually several motivations, incentives, and reasons. First, hardware constraints that prevent us to use JIT compilation. Second, brief executions for which JIT are probably not beneficial. Third, because this is an intriguing research question. Is it possible to build fast JavaScript ahead of time compilers? How fast can they be? So, how to attack the problem? First, by deploying conventional compilation techniques. And, second, by accommodating just-in-time compilation principles to ahead-of-time compilation. The idea is to rely on optimistic compilation. Let us illustrate this principle with the fib function. The fib function will be compiled into three functions. First, a dispatch function that will branch according to the type of the argument. Second, two versions are generated. One specialized version, above with a green mark. One generic version, below with a red mark. The specialized version, specialized for integer arithmetic in this example, is much faster than the generic version because it uses faster operators that do not check the type of their arguments. The central question is how to select the types of the specialized versions? This has been the subject of previous studies of our own. Our proposal is a departure from traditional type inference systems. Instead of trying to infer types according to all possible executions, types are inferred according to efficiency criteria. That is, the compiler assigns variable types that enable the better code generation. Our approach relies on the following assumption. The most likely data structure a program will use, is the one for which the compiler is able to produce its best code. We have established the validity of this assumption in a previous study. To validate the approach, we have built Hop.js, an ahead-of-time compiler for JavaScript. Hop.js compiles all of JavaScript, but it does not optimize the whole language. Some features are not optimized. For instance, evil, or floating point numbers. Remains one major problem. JavaScript is a big language. How to cope with such a large language, for an academic project, managed by a single researcher? The solution has been to compile to another high-level language. Because of the proximity of the two languages, Hop.js compiles JavaScript to Scheme. The generated Scheme programs are then compiled into C. These C files are then eventually compiled to object files or shared libraries. In spite of their proximity, JavaScript and Scheme have significant differences. In this talk, we present two of them. JavaScript functions and Scheme functions are different. Scheme functions are read-only values. JavaScript functions are regular objects that can be extended with new properties. Let us start studying the implementation of the Scheme function. It uses two free variables, CNT and base. The variable CNT is assigned, so it is boxed. It is compiled as shown in the figure. The function is implemented as one heap allocated object, and one heap allocated box for C and T. Here is the similar function implemented in JavaScript. Because it is a regular object, its implementation is more complex than the plain scheme implementation shown in the figure. In addition, extra values are allocated. Obviously, JavaScript functions are much more expensive than scheme functions. To mitigate the problem, we use ad hoc compilation patterns. We present in this slide the one used to compile for each. Instead of passing to for each a fully built JavaScript function, we pass it a stack allocated scheme function. If the array is a plain array that does not override for each, the scheme function is used. If the array overrides for each, the full JavaScript function is allocated and the plain generic for each function is invoked. This is the purpose of the JSArray for each function. If this argument is a plain array, it calls JSArray for each procedure that works with scheme functions. Otherwise, it heap allocates the JavaScript function and calls the standard for each function. This is another illustration of the optimistic principle. Here, we assume that for each is the regular JavaScript for each function, so we speculate that there is no need to build a full-blown JavaScript function. Let us mention another important difference: numbers. Contrary to most general-purpose programming languages, JavaScript only supports floating-point numbers. However, integers play an important role, for instance, for accessing arrays. So the question, how to represent integers? And more precisely, in our case, how to map JavaScript integers to scheme integers? There are at least 4 known possibilities. The simplest solution could be to represent all numbers, including integers, as floating-point numbers. We are not aware of any system designed for performance that uses this strategy. The second possible strategy is Nan Tagging, a technique that takes advantage of all the possible not-a-number values to encode type information. The remaining options are to distinguish integers and reals values using bit patterns. Floating-point numbers are heap allocated and integers are represented as 32 or 53-bit values. We have implemented the last 3 strategies in our scheme implementation and we have measured the performance differences. Unsurprisingly, Nan Tagging outperforms all other encoding for the ALMA benchmark as this program uses floating-point numbers intensively. Nan Tagging saves the heap allocations the other encodings use. Unfortunately, we have not been able to obtain competitive performance for the other tests. This is why Hoc.js does not use Nan Tagging. We must note that this might be due to an insufficiently polished implementation, as some industrial JavaScript implementations use this encoding, with apparently much more successes. The 2 other frameworks, SMI and Int53, deliver close performance but with an advantage to Int53. This is because Int53 takes advantage of a IEEE 754 peculiarity. Above 2 to the 53 only even integers can be represented. In consequence, incrementing an Int53 index never overflows into floating-point numbers. Let us now present some benchmark results. Jetstream used to be a popular JavaScript benchmark suite. We have compared the performance of Hop.js with the performance of Node.js, that relied on V8, with the performance of SpiderMonkey, named JS68, used in Firefox, and with the performance of JavaScript Core, named JSC, used in Safari. The first observation is that Hop.js is about 1 order or magnitude slower than all of the other systems for all floating-point intensive programs such as Crypto, InBody, or Raytrace. Hop.js also performs poorly on DatesParb, but this test uses Evil, a feature Hop.hs does optimize at all. The benchmark Delta Blue also exhibits a pathological performance problem. For the other tests, Hop.js is in between 1.5 times and 3 times slower than the competition. This might be regarded as a weak result, but we have to observe that all systems but Hop.js have been using Jetstream for decades, and as such have spent decades optimizing these very benchmarks. It is then questionable whether these tests are still representative of these systems' performance. For this reason, the major JavaScript implementers have decided to retire Jetstream. This is why we are proposing another benchmark suite that, we think, better approaches JavaScript server-side usages, the application domain targeted by Hop.js. Hopstone is composed of 18 benchmarks. In the interest of time, we use only 16 in this presentation. The tests are coming from different sources and they are implemented by different authors. Instead of presenting the peak performance of each system for each test, we show curves that indicate how systems perform when inputs grow. We think this visual representation better shows the general performance of each system. It would probably be unsuitable if we were interested in comparing few percentage differences, but here, we are only interested in comparing the global performance of each system. The first observation is that which system performs best, varies from one test to the other. The second observation is that apart from a bench that we have already mentioned, Hop.js is competitive. For most tests it delivers performance comparable to those of industrial JIT compilers. Let us zoom in some results. BAG and BASIC show that Hop.js handles efficiently integer arithmetic and simple array accesses. Laval, which uses higher order functions, shows that, in spite of the complex encoding of functions, Hop.js is competitive for allocating and using closures. Marked, which is a markdown parser, shows that although not highly polished, Hop.js implementation of ropes delivers decent performance. Minimalist execution is dominated by arrays obtained by splitting strings. Most of these arrays have very brief lifetime. This pattern is not handled very efficiently by Hop.js that uses a conservative non-copying garbage collector. Moment is a library for dealing with dates for these operations. Hop.js rests on POSIX functions operations that relies on set. This is not competitive with a native implementation. Richard's proxy is the only test that uses proxy object. This test shows that Hop.js is competitive even for tests that use high-level JavaScript features. UUID uses exceptions. The Hop.js implementation that rests on cset jump, long jump, is not as fast as the compared Git compilers. The paper contains analyses of the other tests. In conclusion, the paper presents Hop.js, an ahead-of-time compiler for JavaScript. The paper presents two benchmark results. It presents Jetstream, is an old JavaScript benchmark suite, for which Hop.js is slower than industrial JIT compilers. It also presents Hopstone, a benchmark suite composed of various tests, among which some are currently used in the wild. For the second test, Hop.js shows competitive results. At this point, it is still difficult to conclude if ahead-of-time compilers can or cannot reach the same performance level as JIT compilers. It is difficult to understand if the weak performance of Hop.js on Jetstream are due to the over-optimizations of JIT compilers, or to intrinsic weaknesses of the ahead-of-time approach. You will probably have to make your own opinion. Unsurprisingly, we believe that Hopstone is more representative than Jetstream because Hopstone is composed of programs actually used in real applications. We see the results on the Hopstone suite as an incentive for continuing the exploration of ahead-of-time compilation of JavaScript. Thank you for your attention.
Languages are often formalized as sets of strings. Alternatively, we can consider a language to be a type-level predicate, that is, a function that maps any string to a type of proofs that the string belongs to the language. Each inhabitant of such a membership type is an explanation or parsing. If there are no inhabitants, then the string is not in the language. With this simple idea, we can easily define the usual building blocks of languages. For instance, a string is in the union of P and Q when it is in P or in Q. So memberships are subtypes corresponding to logical disjunction. Likewise, membership proofs for language intersections are product types corresponding to logical conjunction. As a more interesting example, a string W is in the concatenation of languages P and Q exactly when there are strings in P and Q that concatenate to W. While precise and elegant, this definition does not tell us how to recognize or parse language concatenations, since the existential quantification is over infinitely many string pairs. Now, in case you're not used to AGDA, let me point out a few things. Bottom and top are the empty and singleton types. Logically, they correspond to falsity and truth. The type x equals y has a single inhabitant when indeed x does equal y, and otherwise is empty. Some types are written with the disjoint union symbol. Non-dependent product types are written with the cross symbol. Dependent product types are written with the exist symbol. The puzzle addressed by this paper is how to bridge the gap between this non-computational specification and correct computable parsing. Now here's the plan. First, we'll define a normal form for languages. The main idea is to use Berzozowski-style language derivatives at the level of types, which is to say propositions. Next, we'll prove lemmas relating this language normal form to the usual building blocks of languages. So far, everything is propositional rather than computable. That is, at the level of types rather than computational inhabitants of those types. The next step relates our language lemmas to decidable form. Finally, we will apply these insights in two ways to yield dual correct parsing implementations. Remembering that a language is a function from lists, let's consider each data constructor for lists, namely nil and cons. Nullability of a language is the proposition that the language contains the empty string. The derivative of a language P with respect to a leading character A is another language, consisting of the tails of those strings in P beginning with A. The proofs that W is in the derivative of P with respect to A are exactly the proofs that A cons W is in P. The importance of these definitions comes from a simple fact with a simple inductive proof. Given a language P and a string, we can successively differentiate P with respect to the characters in the string, resulting in a final residual language. The original language P contains the input string if and only if the residual language is nullable. This theorem and its proof are shown in the lower left corner of the slide. AGDA is quite liberal with names, and in this case, the name of the theorem is nu composed foldel delta, with no spaces. Note that everything on this slide applies not just to languages, but more generally to functions from lists to anything. The next step in our plan is to identify and prove a collection of lemmas that relate nu and delta to the standard language building blocks. The nu lemmas on the left relate types and are equalities or isomorphisms. The delta lemmas on the right relate languages and are equalities or extensional isomorphisms. AGDA proves the equalities automatically simply by normalization. The others take a bit of effort. All proofs are in the paper's source code. The style of these lemmas is significant. Each one reduces nu or delta of a standard language construction to nu and or delta of simpler constructions. The computable implementations that follow and their full correctness are corollaries of these lemmas. Given a language and a candidate string, we can apply the language to the string to yield a type of proofs that the string is in the language. Now we want to construct such a proof, or show that one cannot exist, and we can express this goal as a decision data type. A parser for a language is then a computable function that maps an arbitrary string to a decision about whether the string belongs to the language or not. Isomorphisms appear in the language lemmas of the previous slide, so we will need to know how they relate to decidability. Fortunately, the answers are simple. If two types are isomorphic, then a decision for one suffices to decide the other, since evidence of each can be mapped to evidence of the other. Likewise for extensionally isomorphic predicates. While we cannot possibly decide all predicates, we can decide some of them, and we can do so compositionally. Together with the isomorphism deciders from the previous slide, these compositional deciders cover all of the constructions appearing in the language calculus lemmas. For example, consider deciding the conjunction of A and B. If we have proofs of each, we can pair those proofs to form a proof of the conjunction. On the other hand, if we have a disproof of either, we can use it to construct a disproof of the conjunction. Let's now pause to reflect on where we are in the story. The language decomposition theorem reduces membership to a succession of derivatives followed by nullability. Our language lemmas tell us how to decompose nullability and derivatives of languages to the same questions on simpler languages. The resulting questions are all expressed in terms of propositions and predicates that happen to be compositionally decidable. It looks like we're done. We just formulate the languages, compute derivatives and nullability, and apply the language lemmas. However, we cannot simply apply the language lemmas by pattern matching, because languages are functions, and so cannot be inspected structurally. What can we do? Exactly this same situation holds in differential calculus, since differentiation in that setting is also defined on functions, and we have a collection of lemmas about derivatives for various formulations of functions, such as sums, products, transcendentals, and compositions. When we want to compute correct derivatives, there are two standard solutions, known as symbolic and automatic differentiation. Symbolic differentiation represents functions structurally and applies the differentiation rules by pattern matching. Automatic differentiation represents differentiable functions as functions that compute their derivatives in addition to their regular values. We can apply these same strategies to languages. Applying the first strategy to languages leads to an inductive data type of regular expressions. To keep a simple and rigorous connection to our original specification, let's index this inductive data type by the type-level language that it denotes. Here I have kept the vocabulary the same, distinguishing type-level language building blocks by a module prefix that appears here as a small lowered diamond. Note that nu and delta here are decidable versions. Correctness of parsing is guaranteed by the types of these two functions, and so any definitions that type check will suffice. Given our inductive representation, we need only define nu and delta. The definitions shown on this slide are systematically derived from the language lemmas shown earlier in the talk, using the compositional deciders. The definitions are to be read in column major order, that is, each column is one definition, given by pattern matching. Applying the second strategy to languages leads instead to a co-inductive type of tries, which is an exact dual to the inductive structure of regular expressions. The language operations are now defined functions instead of constructors, while nu and delta are now selectors instead of defined functions. Again, correctness of parsing is guaranteed by the types, so any definitions that type check will suffice. Given our co-inductive representation, we need only define the language building blocks. The definitions shown on this slide are also systematically derived from the language lemmas shown earlier in the talk, using the compositional deciders. This time, the definitions are to be read in row major order. That is, each row is one definition and is given by co-pattern matching. Remember that this language representation is a pair of a nu and a delta, so a single definition gives both. Now here's the magical thing. Compare this implementation with the previous one. The code is exactly the same, but its interpretation changes, as signified by the syntax coloring, which the AGDA compiler generates during typesetting. What pleases me most about this work? Well, there are three things. First, there is the simple formal specification, uncomplicated by computability. Second, the clear path of reasoning from propositionally defined languages to decidable parsing via decision types. Finally, there's the duality of regular expressions and tries, paralleling symbolic and automatic differentiation, using exactly the same code for parsing in both cases, though with dual interpretations. There are more goodies in the paper. I encourage you to give it a read.